All right, so we're going to talk about vector-valued functions. This is the first section in chapter 13. In 21C, typically we just cover 13.1 and 13.2 just to give you really just a sense of how vector functions work. And you're going to revisit this in 21D. You're going to spend a lot of time working with vector-valued functions. So I'm going to start just because whenever I get a chance to, this is one of my favorite examples to talk about. A vector-valued function can be used to describe a curve in space, and a very interesting curve is called the cycloid. And the cycloid, as the name kind of implies, like a bicycle, you could think of it as the path that a bug that gets squashed on a tire. And as the tire's rolling, if you just focused on the bug, you would see a path like this red path. It's going to look like a series of curves. That is not a half of a circle, by the way. If you look at this, it's not actually a semicircle. Okay. And this path is called a cycloid. The actual Cartesian equation for the cycloid is rather complicated. If you try to get it down into just X and Y, like in other words, how would you find a point on this curve? This is what it is in Cartesian coordinates. Very, very difficult. And one of the benefits of a vectored value function is you can often describe a complicated curve like this in a much simpler way. Okay. And just a little bit, if you've had me before in 21B, I might have introduced the cycloid if you talked about parametric equations, if we got that far. Cycloid seems, on the surface, okay, well, the path that a bug takes when it's squashed on a tire, well, big deal. What good is that? The cycloid has some very interesting and useful properties to it. I'm going to share my screen here and share one thing. So let's see, the cycloid right here. There's the picture up here. That's a nice model to see what the path of a cycloid is. But an interesting property of the cycloid, if you can see this illustration here. If a ball was rolling down a cycloid, if you turn that graph upside down, no matter where the ball starts, all of these are going to reach the bottom in the same time. And that would not be true if you were rolling a ball down, let's say, a parabola or even half of a circle. That would not be true. This is a property of the cycloid. And an interesting application of that is, they mentioned it here, is the early clocks. Early clocks were pendulum, and that would trace out a circle, right? They would follow the path of a circle. And what would happen is that would lose time as the clock, as the swings got smaller and smaller, the time would not be the same. But if you developed a pendulum clock that follows the path of a cycloid, then it becomes an isochronous, meaning it keeps the same time no matter how far, what the amplitude is of the swing of the pendulum. It's keeping the same time. So a very useful curve, which just also can be thought of as the path of a bug squashed on a tire. So kind of an interesting thing how what seems like not a very useful curve actually has some interesting properties. Okay. So back to vector-valued functions. So we saw that the actual Cartesian equation is pretty messy, but if we use a vector-valued function, we have a more reasonable way of writing a vector that will predict where that bug is at any moment in time. If you're interested, you can go back and use, I started labeling on my picture here using some geometry. we want to figure out a point that will trace where that bug is, the XY coordinate at any moment in time. So you can look at this picture and maybe derive separately. The X coordinate would be R times theta minus R sine theta, and the Y coordinate would be R minus R cosine theta. Don't worry about the derivation. At this point, that's not that important. And so if we, just to make it a little bit simpler, if we pretend the radius of our circle is 1, and we replace t for theta, then we have a more standard looking vector valued function. R of t is t minus sine of t. Again, R is 1, and theta is getting replaced with t. And the y coordinate of your vector is 1 minus cosine of t. So now you can think of this as, this will give a vector that points from the origin to where the bug is at over time. You could literally think of t as time, okay? It also represents the angle theta. So this is a vectored valued function for position. So let's see how that works. So what I did here was I drew a couple of curves of what that cycloid would look like. And if you plug in, for example, pi into our position function, you're going to get the vector pi comma 2, which would point to, that would be when the bug is at the top of the arc of the cycloid. That makes sense, because when theta is pi, the wheel has turned half of a revolution. So the bug was on the ground before, now it's up at the top. I did a vector for 3 pi over 2. And then of course 2 pi, that would be 1 revolution of the wheel. So the bug got squashed here. By the time you get to 2 pi, the bug would be on the ground again. And so that vector gives us 2 pi 0. That would be the location of the bug. Okay. Now that we have a position vector function, we might want to know what's the velocity of the bug at any moment in time. What's our velocity function? And of course, borrowing what we've learned from derivatives in 21A, first quarter calculus, if we have a position function, the velocity function is just the derivative of that. So taking the derivative, I get 1 minus cosine of t, comma sine t. And because it is a derivative, we also know the derivative of a function produces tangent lines, right? So my velocity vector will be tangent to the curve. And we'll see that in a second here. Also, you can find acceleration. Acceleration is the derivative of velocity. So if I take the derivative of this, negative cosine becomes sine t, that becomes cosine t. And to see how this all fits together, I calculated the velocity and acceleration vectors at some different t values or theta values. So the velocity vector at pi over 2 gives you 1, 1. So that vector would be tangent to the cycloid at that point. And my acceleration at pi over 2, if you plug that in, gives you 1, 0. So that vector is pointing horizontal. At the top of the arc, the velocity vector when t is pi, plugging in here, gives you 2, 0. That's tangent, that's horizontal vector. And the acceleration vector gives you 0, negative 1, which is pointing actually straight down, isn't it? When the bug comes around and hits the ground again, the velocity vector is actually 0. It's not moving at that point, right? If you can picture that bug going around the tire, when it gets to the bottom, it's not moving there. Its acceleration, however, is purely upward, 0, 1. You'll learn in physics, or if you've taken physics, you might know this already. You know, in terms of motion, acceleration kind of precedes the motion, right? So the bug is here, it's moving in this direction. When it gets to the top, the bug now wants to move downward, and sure enough, the bug does move downward. When it gets to here, what's its next initial motion is going to be to go upward, right, along this arc, and so the acceleration vector is pointing upward. Okay. Oh yeah, and then remember that what is still true, speed we've learned is the absolute value of velocity. For vector valued functions, that would be the equivalent to the magnitude of your velocity vector. So if we wanted to find the speed of the bug at pi over 2, we would take the magnitude of our velocity vector at pi over 2, which was 1, 1, and the bug is traveling at a speed of root 2, whatever units. At t equals pi, my velocity vector was 2, 0. The magnitude of that is 2. That would be the speed of the bug when t is pi. So it's faster, right? That's bigger than this. Okay. So that's the cycloid. I like that just because it's a vector valued function that's kind of interesting and something it's easy to draw and picture that bug spinning around the tire. But there are other vector valued functions. Here is a vector valued function that actually is three-dimensional. That's tracing out a position, a curve in three-dimensional space. So if we want to find the tangent line to that curve, tangent lines, remember you need a reference point. You need a point where the tangent line is going to be drawn, and you need a direction, which is given by the derivative. Of course, the derivative could also be thought of as the velocity. So if we take the derivative of this position equation, we get cosine t, 2t plus sine t, and then e to the t. If we plug in 0 for t, we get 1, 0, 1. Our reference point, where is our tangent line? It's at r of 0. So if I evaluate my position vector at 0, I get 0, negative 1, 1. And recall from chapter 12 how to write the equation of a line in space has to be parameterized. So x would be your reference point, 0 plus 1t, y is negative 1 plus 0t, z is 1 plus 1t. You can also write that as a vector function. Recall from chapter 12, we sometimes wrote our lines as a vector, actually a vector valued function, huh? So we were actually exposed to these types of functions earlier in chapter 12. Now, a series of problems here that are very common in terms of vector valued functions that you'll see have to do with circles. Okay. You recall from chapter 11 in 21b, if you got that far when you studied parametric equations, there are lots of ways to parameterize a circle. And this is a directly related to that. For vector valued functions, there are lots of vector value functions that can trace out a circle. And some of the things that might vary is, where, if it's tracing out a circle, where is it starting, right? What direction is the circle being traced out? Things like that. So for each of these, we've got a few examples that all involve circles. We want to know, where does the particle begin? What direction does it travel, clockwise or counterclockwise? Is the particle moving at a constant speed? And is the acceleration vector perpendicular to the velocity vector? So let's start with this one here. So r of t is cosine of 2t times I plus sine of 2t times j. And so remember, this is your x, what's describing your x motion. This is describing your y motion. Now, recall, why is this a circle? Well, if you took x squared plus y squared, you would get cosine squared plus sine squared, which we know equals 1. So this is just tracing out a unit circle. Where does the particle begin? That would be when t is 0. If I plug in 0 for t, I get the vector 1, 0. So that tells me my initial location of my particle is right there, right along the positive x-axis. To find out what direction the particle is moving around the circle, I want to find the velocity. If my initial velocity is upward, then it would be going counterclockwise. If it's downward, that'll be going clockwise. So if I plug in, where is it? There we go. If I get my velocity vector, which is the derivative of my position vector, -2 sine 2t, 2 cosine 2t. My velocity vector when t is 0 gives me 0, 2. So that's this vector here, that's pointing straight up. And so that would tell me that my initial velocity is moving this way, so it makes sense that the particle is moving counterclockwise around the circle. Yet another way to do it, to figure out the direction of motion, is you could also locate another point, right? When t is pi over 4 or theta is pi over 4, you get the vector 0, 1, which is up here. So if the particle was here when t was 0, here when t was pi over 4, it made sense that it was moving counterclockwise. Okay, so either way, by finding a point or by using your velocity vector. Okay, another question they asked was whether this particle is moving at constant speed. And speed is the magnitude of your velocity vector. So magnitude is the square root of each part squared, the sum of those. And when I square those, if I factor out a 4, I get my identity here that equals 1. So the speed at all times, right, this disappears. The speed at all times is a constant speed of 2. So yes, this particle is moving around the circle at the same speed. And then another question that was asked was whether the acceleration vector was perpendicular to the velocity vector. So my acceleration is the derivative of my velocity vector, which is right here. Recall from chapter 12, how do you tell if two things are perpendicular? Their dot product should be 0. So if I do the dot product of my velocity vector with my acceleration vector, sure enough, I end up getting 0. So what that tells me is all times as this particle is traveling around the circle, my velocity vector is always perpendicular to my acceleration vector. Up at the top, my velocity vector is going purely to the left, my acceleration vector is going down. That's at a right angle. Okay. This might make sense if you're familiar with the idea of centripetal acceleration and centripetal force. When you're traveling around a circle at a constant speed, you're always accelerating inward towards the center of that circle. That's a physics thing. Okay. All right, this one's just to remind you that there's multiple ways, as we mentioned, to describe a circle with parametric equations and thus with vector valued functions as well. Sine of t, cosine of t as a vector also traces out a circle because x squared plus y squared gives you 1. But what's different here is my initial position vector, when I plug in 0, gives me 0, 1. So my particle's starting up here at the top. As far as which direction it's going, I'm going to take the velocity approach. My derivative of my position is cosine of t negative sine of t. If I plug in 0, I get the vector 1, 0, which tells me my initial motion is going to go to the right. So that I can conclude is particles going clockwise this time. Is it moving at a constant speed? Well, the magnitude of my velocity vector is going to give me cosine squared plus sine squared. Square root of 1 gives me 1. So yes. And my acceleration vector, derivative of velocity, dotted with my velocity vector also gives me 0. And so, again, that makes sense. If you're traveling around a circle at a constant speed, your velocity vector should be pointing inward and it will be perpendicular to your velocity vector. One more circle example. R of t is cosine of t squared as a vector, and then sine of t squared is your y component. R of 0 here is 1, 0 if you plug in. My velocity vector, taking the derivative using the chain rule, gives me this. And actually, if I plug in 0, what's kind of interesting here is I get 0 and 0. So my initial velocity is nothing, right? Right at the beginning, I have a 0 velocity. So that isn't going to help. So what else could I do? Well, I could go back and maybe I'll plug in something, bigger than 0. And I chose the square root of pi over 2, thinking ahead that if I plug that in here, I'm going to square it, right? So if I plug in pi over 2, I get the vector 0, 1, which is up here. So if the particle was here when t is 0, here when t was pi over 2, it makes sense that it's going counterclockwise. Now, is this thing moving at a constant speed? Taking the magnitude of my velocity vector, I can factor out 4t squared. That identity is going to give me 1. Square root of 4 is 2. Square root of t squared is the absolute value of t. Now, because this has t in there, you can tell that I would have a different speed depending on my time, right? Depending on what t is. So this is not moving at a constant speed as it travels around the circle. And the result of that, are my velocity and acceleration vectors perpendicular? Well, doing the math gets a little bit ugly. To find the acceleration vector, you need to use the product rule for both x and y, taking your derivatives. Finally, simplify, get my acceleration vector. If you run through the math and try doing the dot product of your velocity with your acceleration vector, I end up getting 4t, which is not a constant, right? Which is not 0, is it, huh? Unless t is 0. That is not always going to be 0. So that tells me my velocity and acceleration vectors are not perpendicular. And, okay, why is that happening? This is because we're not traveling around a circle at a constant speed. The speed is changing. All right. Another very commonly talked about vectored valued function. Now that we know if you see a two-dimensional vector valued function that has cosine and sine, that describes traveling around a circle, right? Cosine t plus sine squared, cosine squared plus sine squared of t equals 1. So this would be traveling around a unit circle. But for this three-dimensional vector, my z component is t squared. And you can see that my z component, as time increases, this is going to get bigger and bigger and bigger. So logically then, to think about what this curve looks like, you're traveling around a circle in terms of x and y, but your z value is getting bigger. So you can picture, it's like traveling around the outside of a cylinder where your z value is constantly increasing. And you get this curve. Some of you may know this name from biology. That's a helix, right? It's a helix. It also looks like the kind of the curve, if you can imagine a plane taking off at the airport, maybe, and doing a circle, climbing upward, right? And so a helix is a very, I couldn't see the bottom of that, apologize for that. Yeah, here's the bottom of the cylinder, and your helix, starting at 0, z would be 0. So it starts here, and as z gets bigger, it's going to go up the cylinder. And so here's another question you could get asked, rather than asking if the velocity and acceleration vectors are perpendicular, but how about just what's the angle between the velocity and the acceleration vectors at pi over 2? So you take your derivative of your position function to find your velocity vector, take the derivative of your velocity vector to find your acceleration vector, evaluate both at pi over 2 to get these two vectors, and recall from Chapter 12, the angle between two vectors can be found as the inverse cosine of the dot product of the two vectors divided by the magnitude of the two vectors. And that gives me the inverse cosine of 2 pi over the square root of 1 plus pi squared times the square root of 5. It's an angle, right? It's some angle there. And I tried to illustrate that, those two vectors right here. Pi over 2 would be right at the side of the cylinder here. My velocity vector is going tangent to the curve. My acceleration vector is moving inward. It's not perpendicular, otherwise this would have been 90 degrees, right? But it is facing upward and inward as well. Okay, one more problem here related to that. So this is kind of a fun problem. Suppose we had a child running down a circular stairwell given by r of t equals 15 cosine t, 15 sine t, and z is 70 minus 5t. Now we can spot this, right? Your x and y, that would trace out a circle. Okay, the radius would be 15 though in this case, right? And then your z value is going to be changing. What is the child's initial height? Well, when t is 0, your z component is just going to give you 70. So child starts at the top at 70 feet, and we can picture this child is running down this helix. When does the child reach the ground? That would be when z is 0. So if you set your z component equal to 0, that's 14 seconds. And what is the speed of the child as the child's running down the stairwell? We know that's the magnitude of your velocity vector. Take your derivative of your position vector, and we'll find the magnitude, the square root of the sum of each part squared. Sine squared plus cosine squared is going to be 1. So you're going to get 225 plus 25 is the square root of 250. So the child is moving at a constant speed as the child moves down the stairwell. Okay, so again, there's just some examples of some vector valued functions. The main thing is knowing what it is and how to find the velocity vector and the acceleration vector. That's going to be the majority of the problems you're going to see in 13.1.